Welcome back to ECE 320A. Homework number 6 is due today, and that is you're solving S-domain problems or circuit analysis in the S-domain, and you're really putting all of these pieces together. Now you can analyze a circuit for all time, and especially if you have switches present. You start finding or determining initial conditions prior to that switch being closed or opened, and then you analyze the circuit in the S domain for non-negative values of time thereafter, and that's what we are using. We're using the one-sided Laplace transform. Today we are going into even new material. I'm assuming now that you are experts on convolution. If you need more material, it's available as supplementary material. It's now within submodules. If you click on those submodules, it will open up and show you many more pieces of notes and videos. If you need a little bit more help on flipping and sliding, if you need a little bit more help on how do I determine the interval of time when this particular expression is valid, what do I use for my limits of integration, all of that with some examples are available to you, and that should help you solve homework number 7, which is due in a week. Our third exam is 2 weeks from today, on the 21st. And before that, I believe we will have a homework 8, and some of this material today is getting us ready for homework 8. Today what I want to do, and I have posted exam number 3 review material. If you want that, this over the long weekend, there is a 3-day weekend. I will see you though again on Tuesday, right? So we don't get a break, or maybe that's a good thing. It is a good thing. And if you want to start studying up for exam number 3, that's available to you on D2L with practice exams. Today what I want to do is, now that we have this S-domain tool available to us, let's look at some active circuits and passive circuits, deriving the transfer functions for those. And we'll actually derive transfer functions for a way to scale signals. That's the nominal inverter circuit. We will also look at low-pass filters. How do we design low-pass filters? How do we design high-pass filters? Or how do we analyze these circuits that actually result in giving us low-pass filter characteristics or high-pass filter characteristics? And then you'll understand how to adjust the break frequency as far as what's my bandwidth on my low-pass filter, or what's the bandwidth on my high-pass filter. That will be clear, hopefully, by our discussion of these rudimentary ideas behind Bode plots. That will be, well, somewhere in there, maybe we'll talk about Goldilocks. I don't know. Who knows where we will end up in today's class, but Goldilocks is known for something being just right. Porridge. And we've already talked about oatmeal, haven't we? Lumped circuits. But now we're going to be talking about Goldilocks, and we can do that in terms of these break frequencies. And we've talked about decades. Decades being a 10, but in this case we're thinking of that 10 as a factor of 10. So a decade from 1 is 10. A decade from 10 is 100. A decade from 100 is 1,000. So we're going to be thinking in these decade steps of frequency. And if I had a break frequency at 5 radians per second, then if I said a decade beyond that break frequency, what frequency would we be talking about? A factor of 10 beyond 5. 5 times 10 is 50. So now if I say a decade beyond the break frequency being at 5, you know you're at 50 radians per second. If I said a decade before 5, now you're dividing by 10. Now you're at 0.5. You're at half a radian per second. And that's actually allowing us to talk about or use this Goldilocks analogy. A decade before is maybe a little small. A decade after is maybe a little too high. But we want to get right in the sweet spot. That's the break frequency. And we're going to be doing approximations based on low, high, and right in the center. That's where Goldilocks comes into this. So now you can go home over the long weekend and talk to your parents and tell them the Goldilocks story. And they're going to be saying, I got lost when you said Bodhi plot. That's okay. You can start talking about frequency response, low pass filters, high pass filters, and you can now start explaining to them their graphic equalizer and how that relates to electrical and computer engineering. We'll relate that hopefully to system response and S-plane diagram, or time domain and frequency domain, where our frequency domain now is in this complex S-plane. What do the poles tell us? What's the dominant pole? What does the dominant pole mean? Sinusoidal steady state response will then come up. We've got this transfer function. We can use it in a lot of ways. Sinusoidal steady state response now means if I shake a linear system at a frequency, what's going to be happening all over that circuit or in that system? It's all going to be shaking at exactly the same frequency. And we'll learn how to use the transfer function h of s. We'll look at its particular response at a specific frequency, omega naught, which is how we're shaking it. And then we'll see what we can determine based on the output. That might be a voltage, it might be a current. We could have many different transfer functions for a given circuit. Let's now look at specific circuits that produce particular behavior. And again, this is the basics or the foundation of filter design. So if you're wanting to learn how to design filters, now you can. After today's class, if you combine them properly, you now have a low pass, high pass, band pass, and band reject if you put them together properly. So let's now look at transfer functions of circuits. And these circuits will actually, we'll be playing with a couple of different types. We'll look at passive circuits. Passive just means that we do not have any active devices in our electronics or in the circuit. So really that means RLs and Cs. Those are passive devices. We don't have to power those or energize those to get them to work. Active in this case means now we have op amps. Can we build circuits out of op amps? Or by the appropriate selection of elements around op amps. Here's our diagram that you should be very comfortable with. Our system, in this case, will be a filter, capital H of S, the transfer function of a filter. Our input to that filter is capital X of S, which is the Laplace transform of the time domain input X of t. This circuit then tells us that we have our output Y of S equal to the product or multiplication of our transfer function description of the system, capital H of S, and the Laplace transform of the input waveform, which we represent as capital X of S. Somebody might write down Y of t, but now how would they write down Y of t in the time domain in terms of H's and X's? So now they would take off the cap lock key on their typewriter if they're typing this. They would unlock their capitals and go to lowercase, wouldn't they? And they wouldn't just directly multiply those, because now they know that, or you guys know from this class, that multiplication in the frequency domain means convolution in the time domain, and that means we need to put that special symbol in there. Let's now look at our circuits that we will build that follow sort of that block diagram, we could put whatever circuit we want in for H of S. Maybe it's a low pass. Maybe we just want to scale the signals. We have a gain circuit. Maybe we want to put together or linearly combine a low pass and a high pass in such a way that we now have a band pass. That's now in our H of S. That's how you can think of this particular block diagram. H of S could be any of these circuits. Let's start with one that we're very comfortable with. Again, we're maybe walking before we're sprinting. We'll sprint in a few minutes. Have 4 of these circuits to work through. Let's look at a passive low-pass filter. And I'm hoping by this point in the semester, you guys could continue on at this point and derive everything we need for this first circuit example. What would this look like in the frequency domain or in the S domain? A passive low-pass filter. Just a resistor and a capacitor. 2 passive elements. We have the resistor, followed then with this capacitor, and we simply take the output as the voltage dropped across the capacitor. The input is applied to that series combination of R and C. In the S domain, the impedance of the capacitor is 1 over SC. Our input is now this capital X of S. And we can quickly write down, so the subscript 1 is for, this is the first circuit. This is our passive low-pass filter. We could do a voltage divider if we needed to rederive this on the fly. We could say, oh, that's the impedance of the capacitor divided by the sum of those series impedances. There's our capacitor's impedance, and then we simply add up the series combination of those 2 impedances in our circuit. If we clean that up a little bit, by that I mean get rid of the denominator and the numerator and get rid of the denominator and the denominator by putting everything over SC and then canceling the SC in the common denominator of the numerator and denominator. Can I do that any quicker? No. But you can do other tongue twisting types of, never mind. So this is 1. Oh, there's some more people going out to the mall. Sorry, I lost them on that. I'm teasing. This is, never mind. There we go. And this is our transfer function. The output, the ratio of the output's Laplace transform over the input's Laplace transform. In terms of a circuit or a transfer function, what form is this in? We have the 2 forms. We have time constant form and pole zero form. Is this telling us what form it's in just by the way it's written? We've normalized this indirectly to have our constant term equal to 1. That's then, in this factor, if all your factors have their constant equal to 1, that's time constant form. So this is now our time constant form. And our time constant is sitting right here. Somebody might call that tau, and that's our time constant in this first order low-pass filter. Passive low-pass filter. And we could write H1 of S. If we now make the denominator polynomial monic, which means make the coefficient of S in the denominator equal to 1, we can do that by factoring out the RC from that. That gives us a plus 1 over RC in the denominator, and I'll push that RC into the numerator, giving us 1 over RC. That's just a constant, S plus 1 over RC. And now this form is our pole zero form. The pole zero form is nice if you're sketching things in the complex S-plane. The time constant form is going to be nice when we're doing Bode plots, when we're sketching the behavior of our circuit or trying to find its frequency response. Then we need them usually in time constant form to allow us to add our terms together. That's the first circuit, and I'm claiming that you now can simply reproduce that in your sleep, that derivation of a passive low-pass filter, first order. Let's now look at some active filters. Here's an active, let's start slow, an inverter circuit. And I think you've seen this in 220, probably, I believe. So now we have an op amp. Let's go ahead and tie that non-inverting terminal to ground. Apply our input through a resistor into the inverting terminal. We'll call this R1, and then we introduce some feedback around that op amp by measuring the output and passing that information back to the input. And here is then all of these reference nodes are the same. Here is now our output V sub 0. If it was in the time domain, there's V sub 0, here's V sub I, there's R sub 1, R sub F, and this particular circuit, because I'm now tying this output back into the inverting node of my input to the op amp, we're actually applying negative feedback. And that allows us then to be operating this op amp under sort of these ideal conditions where we can say we don't have any current going into the minus and plus terminal or the inverting and non-inverting terminal of our op amp, and that V sub n and V sub p, let me call this node V sub n and let me call this node V sub p, their difference is approximately 0, the virtual ground in this case. That's because we have it in negative feedback form. If we want to derive the transfer function for this, which I will do now, just so that we're going to be using this concept over and over again when we replace some of these pure resistors with impedances. And that will give us frequency shaping of our responses, or the transfer function between the input and the output. If we applied KCL at, let's say, this V sub n node, then we have a current going, let's say, to the left through R sub 1. That's going to be V sub n minus, oh, and let's go ahead and do it in the frequency domain. So I'll capitalize this, V sub I, what did I just say, V sub n minus V sub I over R1. That's the current going to the left through R sub 1. The current going into the negative terminal is 0. And the other current that's leaving is this current right there. So I have those two currents. I've already drawn this one, or described this one in equations. To get the other one flowing through R sub F, that's V sub n minus V sub O over R sub F is equal to 0. In this particular circuit, though, notice that V sub P is the same as V sub n with negative feedback, and V sub P is connected to ground. If those are now 0, I can now get rid of, or not have to worry about, V sub n in that one equation. And now I can say that minus V sub O over R sub F, and push the other term on the other side is V sub I over R1. But I really want to write this in terms of V sub 0 of S equaling something. So let me multiply both sides by minus R sub F, and I have minus R sub F over R sub 1 times V sub I of S. And this is my transfer function for the second circuit. And that's simply a way of adjusting the gain between the input V sub I and the output V sub 0. And if you need a positive gain, you could cascade two of these together. And then you don't have a change in the sign of your waveform between the input and the output. Let's now look at another circuit. Now that maybe we're back to feeling more comfortable with analyzing these circuits with KCL, let's look at a low pass filter. But now let's do it by means of an active circuit. Here's our op amp, minus and plus. Here's the output, V sub 0. Here's our input, let me call this R sub 1, V sub I. Again, let me go ahead and connect the non-inverting terminal to ground. And I now want, again, something in the feedback path, but now it's going to get a little bit more interesting. Besides, if I just did this, if I just had an R sub F in there, I would have my inverter circuit. I want to actually put some frequency shaping characteristics in here. And if I add a capacitor C to that, I'm going to be able to do that. So now in my feedback connection, you could think of this as simply some impedance in the feedback path from the output back to the inverting terminal. We're going back to the inverting terminal, so we have negative feedback. Now we can apply all of our op amp behaviors. As far as we don't have current going into the input nodes of that op amp, and V sub P and V sub N are approximately 0. Or I'm sorry, approximately equal, which in this case is 0 because we've tied the positive or the non-inverting to ground. Well, the first thing, if we're going to analyze it in the way that we did last time, why don't we go ahead and simply compute the impedance in the feedback path? And you've done that in today's homework, I believe, didn't you? You were connecting impedances together, so now you have R sub F in parallel with the impedance of the capacitor, which is 1 over SC. And if you do that, you now have R sub F over SC, or the product of those two, over the sum of those impedances, which is now R sub F plus 1 over SC. And we like to clean that up so that we now have S R sub FC, there's another RC time constant that we're used to seeing, plus 1. And here we have R sub F. So that now our impedance in the feedback path is giving us some frequency behavior. It's not just one fixed resistor. We've replaced R sub 2 with something that has some frequency shaping properties. So let's see what that does to us in terms of our transfer function. We now know, though, from that second transfer function derivation, if I want the ratio of the output voltage to the input voltage, in this case, that's just minus Z sub F, that's actually a function of S, over R1, isn't it? Our other one was minus R2 over R1. We've simply generalized R2 to be an impedance, which we now know is Z sub F. If we now plug in the Z sub F, and let me go ahead and put that R1 into the denominator of the numerator. Is that making any sense? I now want minus R sub F over R sub 1 over S R sub F C plus 1. And that's now my my third transfer function. This is h sub s, h of s sub 3, or h sub 3 of s. Do I have a time constant in that circuit, or in that transfer function? Does this look like the low-pass filter transfer function from our passive circuit structurally? What was it? That was here. So in time constant form, that was 1 over SRC plus 1. Now we have the denominator the same, but because of this RF and R1 and the connection that they are here, now we have some gain in addition to the low-pass filter behavior that we have in the denominator. Here is our time constant. And maybe we call that tau sub 3 because this is our third transfer function. Now we want to try to understand this transfer function a little bit, and somebody might say, oh, does it have a DC gain? Well, we could look. DC we know is the frequency is 0. S is equal to 0. We plug in 0 for S. This now looks like that basic inverter circuit at low frequencies, at DC. When Goldilocks is in the small chair, right? This is DC. This is at low frequency. Then we could say at high frequencies, what's going to happen in that denominator? If we let S, now we're thinking S is j omega, and we're walking up that imaginary axis, and we've gone quite a ways up that imaginary axis. Let's say a decade beyond the break frequency. What's the break frequency in this transfer function? It's equal to the pole. Can you tell me where the pole is? That's where we're calling the break. That's where we're saying things are going to be just right in the Goldilocks sense. We want the imaginary part, which we'll have when we replace S with j omega, we want that to equal the real part. When the imaginary part and the real part are equal, that's when we're at that sweet spot. In this case, we're saying what value of S causes all of that magic to happen? Minus 1 over R sub Fc. So that 1 over R sub Fc is the break frequency. Our time constant is the reciprocal of that. Our time constant is Rc. Our pole then, so we have a DC gain of R sub F over R sub 1 with a negative sign, if that's important. Our pole that you've just told me we can find by setting the denominator equal to 0 and solving for S. And that's where nice, fun things are going to happen, or important things are going to happen in terms of the behavior. And I've now been saying that our break frequency is related to that. That's, let's say, omega sub b is 1 over R sub Fc. Don't worry about the negative sign. The negative sign tells us we're in the left half plane, but the distance that pole is from the origin is just that distance, 1 over R sub Fc. And that's our break frequency. That S is a frequency. If we sketched the Bode plot of this, we really only have one break, don't we? We only have one singularity. We only have one pole. There's no zeros, finite. There's only one pole. We have a first order filter. At low frequencies, at DC in particular, we found the magnitude to be what? Minus R sub F over R sub 1. So if we wanted that magnitude in dB, we would take 20 times the log of the magnitude of R sub F over R sub 1, and that's what this value would be. So if R sub f over R sub 1, if R sub f was 10 times the size of R sub 1, we have the log of 10, which is log of 10 base 10 is 1, so we're at 20 dB. If R sub f was the same size as R sub 1, their ratio would be 1, log of 1, 0. So now we're at 20 times 0, or 0 dB. So we're not amplifying or reducing if the two resistors are equal. Anything low frequency at the input is not going to get scaled in amplitude at the output. That's what that's saying when you're at 0 dB. Is that making sense? And we can now adjust that. We could attenuate at low frequencies by selecting R sub f over R sub 1, or we could amplify at low frequencies. Then in our straight line approximations, we're trying to sort of just get a real rough idea of what these filters look like. This is our break frequency, omega sub b. That's where things start to be different, or that's where we consider them to be different. This, in this case, is the 1 over R sub fc, or 1 over tau sub 3. And if we look back at this transfer function right here, and we say, okay, what's going to happen at really, really large frequencies? When S gets big, this S R sub fc is going to dominate 1, isn't it? It's going to be much bigger than 1. And so as omega, which we're going to replace S with j omega, as omega gets big, this denominator is going to get huge relative to the numerator, and we're going to be falling off with omega, aren't we? We're going to get smaller and smaller because the denominator gets bigger and bigger as omega gets bigger. The denominator getting bigger, we divide that into a fixed numerator, the whole thing gets smaller. So our magnitude is rolling off at high frequencies. That roll-off rate is 20 dB per decade, or per factor of 10. And this is where we make that transition, is right at the break frequency where the denominator, real part and imaginary parts, are equal. This is now sloping at 20 dB per decade. If I had a bandwidth, let's say, of 5 radians per second, and now I said, what's the magnitude, and let's say that I selected R sub f and R sub 1 to be equal. Our DC gain is either 1 in absolute terms or 0 in dB. So you're right either way. It's 1, your DC gain is 1 in absolute terms, or it's 0 in dB. That's at DC. So we're coming along, we're at 0 dB, and now I say we break our low-pass filter at 5 radians per second. For whatever reason, that's how we've designed our low-pass filter. Now I say, what's the gain of your filter at 50 radians per second? "50 is a decade beyond 5, isn't it? So you're now this factor of 10, and now that's a decade, so you're 20 dB down from where you were at DC. So you're at minus 20 dB. If I said, where are you at 10 radians per second? Well, I don't know. You told me decade. But we also know that this is equivalent to minus 6 dB per octave. Haven't we talked about an octave? A change of an octave, what's that a factor of? In terms of keys on the piano, maybe it's 8 keys, but in terms of frequency underlying those keys, if you had an A above middle C, is that at 440? 440 hertz for all you musicians, which I am not, but I'll play along. This has to be entertaining, right? Oh boy. So now we're at 440. Where were we? Oh no, we're at 5 here. An octave above 5 would be a factor of 2. So if I'm at 5 and I say, what's your gain an octave above 5? First, what's the frequency that you're at? A factor of 2 beyond 5, you're at 10 radians per second. So now you are an octave above your break, you're at minus 6 dB. So this is now a factor of 2. You can use those to your advantage. An octave is not going to, it's going to break things up in finer and finer resolution. So if I said 2 octaves above 5, where are you? 1 will get you to 10. One more factor of 2 gets you to, I have to take my shoes off. I picked 5. That was convenient, wasn't it? So 1 octave gets us 10. 2 octaves, another factor of 2, that gets you 20 fingers and toes, right? So 2 octaves above, and what's the gain 2 octaves above in this low-pass filter? Minus 12. And 20 is less than 50, so that makes sense. We were at minus 20 at 50. Is everybody okay with this idea? So now if somebody says, design me a low-pass filter with the following characteristics, you'll be able to start thinking through what that means. First order just means we have 20 dB per decade, or 6 dB per octave. If we had a second order, then we're doubling those. If you needed to roll off more steeply, make your transition into the stop band sharper or more sudden or more abrupt, then you're going to need a bigger order filter. If you had a third order filter, now we're screaming down at minus 60 dB per decade. That's quite a bit. So at 50 now, if we had a third order filter, we would be at minus 60, and minus 60 dB is a lot less than minus 20, because we're talking dBs, right? In terms of amplification, a factor of 10, if we had a gain of 1, that was 0 dB. If we had a gain of 10, where are we at? 20 dB. A gain of 1,000, I went too far. A gain of 100, so we went from 0 to 20, that was 1 to 10. 10, another decade to 100, that's 40 dB. So 40 dB is a factor of 100 in absolute terms of gain. 60 dB is a factor of 1,000 in absolute gain. Is that okay? All right. So there is filter number, or transfer function number 3. Let's look, and that was a low pass. Let's look at a high pass. And there's many ways of building these, but this one is designed to help you with a subsequent homework assignment. Maybe not on 7, but maybe on 8. Let's look at this next filter. Let's say that here is our op amp. You didn't have energy storage elements around your op amps in 220, did you? Energy storage. Did you have inductors and capacitors floating around your op amps in 220? I don't think so. So you're learning something today, is what I'm trying to say. Now we're not going directly to ground through that V sub P. and we're actually going to inject our input through that non-inverting terminal. But we want to have negative feedback. So let me label these. Let's say this is R sub 1. Let me say this is SL in the frequency impedance sense. Let's call this R sub 2. And let's go ahead and make our feedback resistor to give us negative feedback. We'll call that R sub F. And here is V sub 0. And again, this is relative to the same reference, although sometimes I get sloppy and I don't indicate that negative reference in the polarity of V sub 0, but that's where we're at. This now, and in the homework, maybe what you'll have is maybe you'll have some more frequency stuff in the feedback path, but you know how to treat that if you understand this design, because you'll just generalize the R sub F to an impedance, Z sub F, and follow through the S's wherever they belong or end up. Let's analyze this. Well, it was pretty straightforward when we were just dealing with things connected to the inverting terminal of our op-amp. Now we've got a mixture, but with the negative feedback and the ideal op-amp assumption that we have no current going into these inverting and non-inverting nodes, we pretty much have just an isolated series circuit in the bottom picture or portion of this diagram that's connected to the non-inverting terminal. So let's examine that circuit. Let me say that this node here is V sub P, and this current, I could say, is I sub P, but that one we're assuming is 0. Here is another node, V sub N, and this current, I sub N, but with the ideal op-amp assumptions, that one's 0 also, and that's going to be beneficial to us. So let's examine this sub-circuit that's down in this lower left-hand corner, and I'll call that, let's examine the V sub P sub-circuit, and we're able to do that because I sub P is equal to 0. So that's a good thing, which says that we can really just pull that piece off and look at it as if we were doing a classical circuit problem. What did we call that? Was it R sub 1? We now have that circuit, and you should be able to do this analysis in your sleep. This is another voltage divider, isn't it? So if we solve this circuit, I can solve for V sub P. That's the impedance of the inductor, which is SL, divided by R1 plus SL times V sub G of S. That's not in any of the forms. That's a mixture of everything. It's not time constant. It's not pole 0, is it? Because I have a non-constant, or I'm sorry, my constant is not 1 in the denominator. Wait, so before I go any further, though, what can you tell me about this circuit? Can you tell me the order of this circuit? So this little transfer function, what's the order of this little transfer function? The order depends on the degree of the denominator polynomial, doesn't it? What's the degree of the denominator polynomial, or what's the highest power of S in the denominator? That's 1, isn't it? So this is first order. This is a first order circuit. the description, though, we haven't normalized the constant to be 1, so it's not in time constant form. We haven't normalized S to have a monic or a constant of 1 for the S, so it's not pole zero form. This is kind of nothing in terms of our forms. Let's put it into both forms. Let's put it first into time constant form, which we can do by making that constant in the denominator equal to 1, which means let's factor out an R1 from the denominator. So if I factor, well, let me write it in the form that we're used to writing it. So I'm going to now say SL plus R1 and put the constant over here. Then I'm going to say, oh, I have SL, but I factor down an R1, so I need to divide that out, right? And I'm going to move that R1 upstairs because I don't want it downstairs. And I now have S, L over R1 over S, L over R1 plus 1. That's H sub 4 of S. And what form is this in? This is our time constant form, and our time constant now is that L over R. That's a time constant. In a capacitor, first order, it was RC. In an RL circuit, our time constant is L over R. So this is time constant form. And for grins, if we wanted to, we could put that in pole zero form pretty easily by factoring out the L over R1 from the S. And if we factor out the L over R1 from the denominator, that cancels the L over R1 upstairs, and we end up with S over S plus R1 over L V sub G of S. And that's the same high-pass filter. That's still equal to H sub 4 of S. I didn't do anything but manipulate some terms within that transfer function. This is now our pole zero form. And we could actually, where were we? We've just analyzed this subcircuit, haven't we? Down below. But what do we know if we disconnected all of that? If we just connected V sub P to ground and forgot this circuit, what do we have remaining? Do you recognize that circuit? If we disconnected what we just analyzed and replaced it with a line to ground, what kind of a circuit would we have? An inverting amplifier. So now whatever is appearing at V sub P is essentially going to go through an inverting amplifier. So now we've introduced a little bit of a scale change or a gain change on top of this filter behavior that we derived in the lower left-hand picture. So we're not quite done, but we could even just analyze this in terms of its frequency behavior. Can you see what's happening here? At low frequencies, what's happening in the denominator? And maybe it's easier to go back to the time constant form. At low frequencies, what do I get in the denominator? What number? Do I get anything? Does it vanish at low frequencies? The denominator? I set S equal to 0, and what do I get in this time constant form? 1. So my denominator is well behaved at low frequencies. That means my transfer function here is well behaved because I'm dividing by 1. Basically, I can forget the denominator. What happens in the numerator at low frequencies? At DC, it's 0, isn't it? And then as I increase the frequency, what happens upstairs in the numerator? It goes up, doesn't it? The S in the numerator, it just keeps climbing and climbing. I have a microphone on. I'll just go outside and you guys can listen to me. I had to do that since I was upstairs. But now, that was what? That was a 0 in the numerator, allowed us to build up from nothing and go up. That's what it's doing. But eventually, this denominator is going to get bigger than 1, isn't it? When I get frequencies large enough. What's my break frequency in the denominator? That's R over L, isn't it? That's my break frequency. So at Goldilocks, at R over L, my denominator, real part and imaginary part are equal. That's where I need to start worrying about the denominator. But until that point, my numerator is just climbing up. It's climbing up from really far down, 0, which on dB, we never reach, do we? We just keep coming up from minus, minus, minus dB. And then at the break frequency, we level off. What's this going to be shaped like then? In terms of frequency behavior, that numerator, 0 at the origin, that's a finite 0, that's a thumbtack right at the origin, right at DC, and then we climb up, don't we? And instead of going outside, we go flat. And this happens where? That's our break frequency, which in this case is R1 over L. And we just had 1, 0 at the origin, so this is going up at plus 20 dB per decade. And at high frequencies, does this make sense? What happens in this picture at high frequencies? In the denominator, the S term dominates, doesn't it? And in the numerator, I just have an S. So I now have S over S, and they're both going off to infinity together. Your gain is 1, isn't it? So in dB, that's 0 dB. Are we getting the feel of this? Why you want to know about limiting behaviors, etc.? Now, let's connect this up. This is one part of this overall circuit. Now we need to connect this up. Let's do a KCL right there. And then we'll tie it all together because we know V sub n and V sub p are the same if our ideal op amp and with negative feedback. We haven't saturated things. So now we're ready to connect up that left-hand corner high-pass filter behavior with the rest of the circuit by performing KCL at V sub n. At V sub n, we have V sub n minus 0, because over here we have V sub n minus 0 over R sub 2, plus V sub n minus V sub 0 over R sub f equaling 0. And from this, I can say, well, I have a 1 over R sub 2 plus a 1 over R sub f. That scales or multiplies V sub n. And then on the other side, I have V sub 0 over R sub f. Or if I solve that for V sub 0 by multiplying both sides through by R sub f, I have R sub f over R sub 2 plus 1 times V sub n of s. And if I call this, did I call one of these H sub 4s? Did I get ahead of myself? I did. This isn't quite H sub 4, is it? Because H sub 4, I would want that to be the entire circuit. So let me call that H sub p. That's just the p part of my circuit. Let's call this one H sub n of S for the positive and negative nodes of my op-amp. That's where that notation is coming from. Now I want V sub 0 in terms of V sub G. But V sub G I have in terms of V sub P, but V sub P is equal to V sub N. Meaning, I can now combine all of this together. V sub 0 of S is actually H sub P of S times V sub P of S. But V sub P of S, was that, no, keep me honest here. What do I have? I was getting distracted. I went outside and then I can't get back on track. Here's H sub n, V sub n, right? So this is now H sub n, but what's V sub n? That's the same as V sub P, isn't it? So that now I have a way of expressing V sub P in terms of V sub G. And this whole piece right here is the H sub 4 of S. And if I put all of those pieces together, what do I have? H sub n was just this R sub F over R sub 2 plus 1, and the other piece, depending on how I want to put it together, let's say it's this piece right here in pole 0 form. That's my H sub P of S. I now have for H sub 4 of S, I have S times R sub F over R sub 2 plus 1, and down here I have S plus R sub 1 over L. And this is the H sub 4 of S. And how does this transfer function, how is it shaped in terms of its frequency response? What's the order of that filter for H sub 4 of S? It's first order, isn't it? Do I have any finite zeros? I have a finite zero. I have one of those, and it's at 0, isn't it? And my finite pole is at minus R1 over L. And that's going to be my break frequency. And now I would just have to worry about that gain, R sub F over R sub 2, but I still have something that looks like that in shape. It may be shifted up or down, but I'm at high frequencies. What do I have? A constant, R sub F over R sub 2 plus 1. So whatever that ends up being, that's going to adjust this amplitude or gain value at high frequencies. And without specifying that, I still know that this is my break frequency, omega sub B, which in this case is R sub 1 over L. I'm still climbing up from the bottom at plus 20 dB per decade, and this piece right here is going to be the 20 times the log of that magnitude. Well, you know what? I don't have that denominator in time constant form, so I'm not going to do that. I'm not going to even do that. Okay? So leave it at that. I'm going to not know what that is. I would just have to evaluate that. Questions on this? What have we done? We've designed low-pass filters, an inverter, and what did I say? High-pass or low-pass? Remind me, I'm falling asleep just like you guys, apparently. What do I have? Low-pass, high-pass, inverters. And I can combine low-pass and high-pass to get a band reject or a band pass by either cascading them or putting them in parallel. That will give me those two different behaviors. So I now can design 4 different filters, just based on today's lecture. Let's look at, are there questions on that? Had you seen that before? Yes. So the question was, what's the difference between a band pass and a band reject? What would a band pass filter look like, shape-wise? It's wanting to favor a certain frequency interval, isn't it? So it might look something like that. A band reject, on the other hand, depending on what it's doing at the low and high end, it might just be doing something like this. Or it might be even more exaggerated. And it might be called a notch filter if it's really deep and narrow. So you might be hearing a notch filter used. But that's the difference between a band pass and a band reject. Questions on that? And you can get these by combining the low pass and the high pass in a cascade or a parallel type configuration. Let's look at the response of systems. Now that you should be getting comfortable with talking about circuits in a schematic way, in a S-domain way, and maybe even in a Bode plot way, in a frequency response way. Let's look at the response of systems and S-plane diagrams. Or time domain versus frequency domain, really. So here we have our time domain. And here is our frequency domain, or S domain. Suppose we looked at this just through a passive low-pass filter. You can get a lot of useful information just out of one device, and that's this passive low-pass filter. In the time domain, what's the impulse response of a passive low-pass filter look like? Or if you've forgotten, you go, wait a minute. I don't remember, but I do remember what it looks like as far as a transfer function. What did it look like as a transfer function? Do you remember? Let's say it's in pole zero form. If you had this lecture in front of you, you could just scroll back, couldn't you? If we had it in pole zero form, which is easier to be thinking about taking the inverse Laplace transform because we can immediately see the pole, we now have our low-pass filter as 1 over RC over S plus 1 over RC. If that's the case, what's our impulse response? It's just the inverse Laplace transform of capital H1 of S. It's going to have a scaling factor of that 1 over RC, and it's going to have an exponential decay determined by this minus 1 over RC t, or you might see that as 1 over RC e to the minus t over RC, or you might see that as 1 over RC e to the minus t over tau. And if we picked some numbers, let's say that we said that we selected RC to be 1/10, or this is now 10 e to the minus 10t for t greater than or equal to 0. That's if we pick the time constant to be 100 milliseconds, 0.1 seconds. That's our time constant, RC. If we needed to sketch that in the time domain, you should be able to sketch an exponentially damped curve. What am I at, and now just remember this is time. At time 0, what is h sub 1 of t? That's 10, isn't it? My pen stopped. That's a 10. There's not a decimal point in there, although my pen seems to think but once I start writing, I think that decimal point will go away, that virtual point. It's 10 for an amplitude. What's the time constant in this circuit? Pardon? 1 over 10. I said it right here, didn't I? RC was 0.1, wasn't it? So how long do I have to wait before this impulse response is gone, effectively? 5 time constants, right? So 5 times 0.1, or in half a second, this circuit is finished acting or behaving in half a second. Did I say 5 seconds? No? Okay. In 5 time constants, 5 times 0.1, in half a second, this circuit has finished its response. And if I could draw that, then this particular point is roughly 5 time constants, 0.5. And that looks fairly impulsive, doesn't it? What's the impulse response? The ideal impulse. I'm sorry, this is the impulse response. What's the ideal impulse look like as a function? It's really, really tall, and then it's nothing, isn't it? And the more our circuit's impulse response looks more like that ideal, the more our output is going to look just like the input. The worse this is, this impulse response of our circuit, at duplicating or imitating the ideal impulse function, the more blurred or different our output is going to be from our input. So if I said, oh, our impulse response is 100 e to the minus 100t, that's even more like an impulse response, and our output will look even more like our input. If I put in a square wave, the output's going to look more square. As I get more and more low-pass filter behavior, I'm going to round off those corners, aren't I? Remember our sort of rounded tail from last time, and then we tailed off? That was because we maybe had a low-pass filter behavior, or more low-pass than something like this. Where are we in the frequency domain? What does this look like? This now has pole zeros, doesn't it, in the S domain, our S domain diagram. If I sketched that, what do I sketch? Here's the real part of S. Here's the imaginary part of S. I want the pole zero diagram because I want to think about the circus. The circus tent, this rubberized sheet on top of infinitely tall poles and thumbtacks. Thumbtacks being our finite zeros, our poles, infinitely tall poles holding up this rubber sheet, are our poles in the transfer function. Where's the pole in this particular case if I now have h sub 1 of s as 10 over s plus 10 to be consistent with little h sub 1 of t. So now I'm over here at minus 10. If I had a slower filter or a shorter bandwidth filter, that minus 10 would be getting closer to the imaginary axis, wouldn't it? Maybe it's at minus 2 or minus 1. Then that's a much lower bandwidth filter. If I had a higher bandwidth filter, then I'm out beyond -10. I'm maybe out at -1,000 radians per second. And that's where my break would be. And that tells me my bandwidth of my filter. What if I now introduce an input to our system? That's just our system right now, the impulse response or the transfer function. What if I applied an input to that, which was x of t, and maybe the input is e to the minus 2t u of t? What's that look like in terms of the time domain response? Where do I start it responding? In terms of, let me just say I'm looking at x of t now. This has an amplitude of 1, doesn't it, at 0. And where would that be finished displaying any kind of noticeable response? What's the time constant here? It's 1/2, isn't it? It's whatever is in below t to get me a -2, or that 2. So if I divided t by 1/2, I would get a 2. So my time constant is 1/2. How many of those do I have to wait before I don't really see anything? 5 will get me below 1% of 1, so that's at 0.01. I'm not going to probably be able to see that. And that will be 5 halves. 5 times a half, right? So 2.5 seconds. This is much slower than my system response, this input. My input was done in half a second. I mean, my system responds quick enough as to be done in half a second. What does this look like in the S domain? If I simply sketched this x of s in the frequency domain, where is it? It's at -2, isn't it, as a pole? So now if I wanted to look at the output of this system, in the time domain, I needed to convolve h of t with x of t. I'm convolving two exponential decaying waveforms. In the frequency domain, if I looked at the S-plane picture of my transform for capital Y of S, what does that look like? I simply combine my poles that I had for H and X. So I have a pole at -2 and a pole at -10. Because this now, Y of S, is this 10 over S plus 10, and my X was 1 over S plus 2. Now do you know what the output is going to be? How would you find capital Y of S to find Y of T? You would do a partial fraction expansion, wouldn't you? And if you did that, if you said, oh, expand on your calculator, hopefully you'll see, whoops, something like the following. You would have 10 over 8 over S plus 2 minus 10 over 8 S plus 10. Now can you tell me what Y of T is? And you know what that looks like. You have e to the minus 2t, and taken away from that is e to the minus 10t. What if, so now we could just go on and on. There's nothing happening this weekend, so you guys can just stay in your chair. We might have to call out for food. Maybe we'll order a pie or something. I know I'm not very healthy. What happens if our input is this? What would you look at in the, or what would you see if I said, oh, show me the S-plane pole zero diagram with an input of x of t equal to a cosine omega naught t and a transfer function of that 10 over s plus 10. I'll do the easy part. That's what you have with an input that's a sinusoid, right? You have poles right on the imaginary axis, and that's going to continually shake your system. What we want to do the next time is to figure out how we can quickly analyze our transfer function and find the time domain sinusoidal steady state output when we excite our system with a sinusoid. Enjoy your weekend. I'll see you on Tuesday. Don't forget your homework is due today.